All right, Kaden said number 12 gave her issues.
Yeah.
Oh, that's a lot then. Well, I hope I can do it.
We have to like prove.
I could have tried harder, but I didn't.
Oh, okay. I tried to give you guys a hint. That one, you're going to see it done and you're like, oh, I'm stupid. Why didn't I get that? No, it's just, you got to put in the right frame of mind. It is pretty easy, but I would absolutely anticipate some people, if you don't go down the road that they want you to go down, then it's a bit challenging.
How?
All right, so 174.
I can't remember which proof we did in class.
Yeah, well, that's why I made it a point to remind you.
We did 11.
So 5-5 is I got to show that that was the one you had problem on? Really? I thought it was going to be 5-6. You got 5-6?
You did.
We did 5-6
We did 5-6 in
in
class?
class.
Okay. All right. I'm going to make you feel bad then.
Okay.
5-5. If one pair of opposite sides of quadrilateral are both congruent and parallel. So I draw a quadrilateral. I got one side that's both congruent and it's parallel. All right, Bailey, what are we going to do? You should know by now. What are we going to do? Let's make triangles, right? So if I literally just do this right here, right? Turn your head to the left. If this is parallel to this, and it's cut by a transversal, what can you tell about that angle and that angle? They're congruent. So I know that that angle is congruent to this angle. And then, Bailey, we got, what's the tried and true thing we do? When the two triangles are next to each other and they share a common side, if they share a common side, what can you immediately say about that side? The same thing we've done for at least, I don't know if it's 20, but it's darn close to 20. It's reflexive, right? Therefore, Cadence, what do we got? We got a side angle side, and you're done. Well, you're done after you say that this side is congruent to this side. Therefore, you could claim what theorem was it? 5-5, 5-4. I'm done. Okay. That's how I would do it. There may be a different way, but that's how I would do it. Anybody else? Okay. Let's grade this real quick. All right. So number one is, well, they show that all the opposite sides are parallel. That's the definition of parallelogram. Number two, they show that opposite sides are congruent. Well, that's theorem 5-4. Number three, it's this one right here. They're showing that one pair of opposite sides are both congruent and parallel. That's 5-5. Number four, a little bit more challenging, but you can tell that they're talking about segments. Well, they're showing that the segments bisect each other. Therefore, that's 5-7. 5-6 has no friends. Oh, wait, it does. Number 5 will be 5-6. 5-6 is showing that opposite angles are congruent. All right, that's 1 through 5. 10, I will look at your proof. 11, 12, well, the rest are all proofs. So I will look at your proofs. All right. Hey, I don't want to demean anyone or say anything, but I'm saying you guys should be catching on that it looks like we've been doing the same proof for at least 3 weeks. You set up two triangles, you show the triangles are congruent by one of the 5 things, and you claim CP, and you're done. Today is no different, right? We're going to continue on that path as well, too. I will introduce one new thing today, but it's got that same flavor. This reflexive thing, whenever you set up two triangles, and as soon as you hear, look at two triangles, either be thinking vertical angles, if there are vertical angles. Sometimes, remember, you have this configuration where you have the true triangles. Can I draw this right? Yeah. Two triangles that look like this. When you see this shape right here, the bow tie, you're thinking vertical angles. Where you're seeing two triangles next to each other, they share a common side, immediately reflexive. You may not even know if the two triangles are congruent, but you should be thinking reflexive. Those are the things that every student in here should be able to do when they look at the shape. Oh, I see vertical angles. Oh, I see reflexive. You may not know how it's proven, but you should know, I see reflexive, I see vertical angles, And I know triangles are grouped by one of 5 things: SSS, SAS, ASA, AAS, and hypotenuse leg. Okay? All right. Today's a tough day. Tough day, and it ends very easy, but it's a tough day in the middle. This is going to seem crazy. It's going to seem crazy what we do. Sometimes, in order to get to something useful, we got to do some really challenging and hard work. That's what we're going to do right now. We're going to spend the entire class on some crazy proofs, right? You got to stay with me. I'll bring it all together at the very end, but it is crazy in the middle. It's also not very useful in the middle, in the sense of, I'm going to show you a couple proofs that you'll never see again the rest of the book. We're going to use those proofs in order to get to something we can use. Okay? If this was not a geometry class, I would skip right to the end. In, I don't know, 5th, 6th, or 7th grade, you were told that the circumference of a circle was equal to 2 pi r or pi d. Your teacher never proved it to you. Your teacher never said, let me show you why this is so. Your teacher just said, write this down, use this formula. Geometry is not that course. Geometry, I can't show you anything that I can't prove to you. So if you're wondering why we're about to do 3 really, well, one easy one and 2 hard ones, if you're going to see, you're going to wonder why we're doing all this, and you're like, I don't know what's going on, you will at the very end. It's because I can't just say, let's just jump to the end and let me give you a formula, this is why it works. Or use this formula, and not tell you why it works. Okay? All right, tomorrow, big day, right? We're going to take what we learned on 5.1 and what we learned today at the very end, and we're going to review that whole thing. We're going to learn everything, or we're going to review everything we know about parallelograms, and today we're going to get one thing about a triangle. Actually, we get 2 things about a triangle, but only one of them is really useful. One's cool, but one's very useful. So tomorrow is the key to passing the quiz. Tomorrow we'll spend the entire classwork on I think I put 40 questions on a 40-question review sheet. And the review sheet is what we did in 5.1, those 4 special things about parallelograms, and the one thing that I'm going to get at the very end of the class. Okay, 40 questions. I will make the quiz off of that worksheet. Okay, I'll just take a couple questions and I'll pick some medium ones, maybe one hard one, and we'll make that the quiz. We'll discuss it tomorrow, and then that'll be then I'll do 5.4. All right, here's your homework. Once again, the homework is about one tiny thing at the very end of class. Everything that happens between now and the end of class is to get us to where I can prove the thing that's useful. But everything in between is a little messy. And they are challenging proofs, not the first one, but the other 2 are very challenging proofs. They're not high school proofs, they're more college proofs. But you'll understand the proof, right? But coming up with it all by yourself would be a stretch. That's kind of insulting, but I don't think I could have come up with this all by myself. I could have stared at it forever and I never would. As soon as I see what they do, I'm like, oh, okay, yeah, but coming up with it all by myself, I don't think I could have done it. All right, ready? All right, so theorems involving parallel lines. So we went from quadrilaterals to parallelograms. Now we're going to parallel lines. We've seen parallel lines before. Alternate interior, same side interior, alternate exterior, corresponding. So these are going to be theorems involving parallel lines. However, they're going to involve parallelograms and triangles. All right, here we go. So lots of theorems today, 4 of them, only one of them is useful, and it's the last one. But the ones in between lead up to it. All right, so first one, and this is the easiest one. Okay, so this is, well, let's see. I've got 2 parallel lines. Remember that the 2 red triangles here mean that the 2 lines are parallel. And it looks like I got perpendiculars to those 2 parallel lines. We're asked to prove that the distance from A to C is exactly the distance from B to D. In other words, we're proving that if you pick any 2 points randomly on 2 parallel lines and you measure it, and then you repeat the process, you better get the same thing. In other words, we're proving that parallel lines never come in and intersect each other. They always stay equidistant from each other. That's what we're proving. Well, we proved that for any 2 points. We never proved it for an additional 2 points. So we're going to do it. It's pretty easy to do. All right. Well, we got our given. We know this is how it's going to end. How do you ever show, what's the easiest way to show that two things have the same measurement? When there's no numbers here.
Triangle.
Okay, I like that thought. Triangle, right? But in reality, when you have a triangle, are you showing that the measurements are the same, or are you showing something else the same? In other words, you're showing that they are corresponding parts are not that they're equal, that they're congruent. Notice on our picture here, we have no numbers there, right? So I don't know how you'd prove, well, I'll take my ruler. That's not proof in geometry. We're going to show that these two red lines or segments right here are congruent. And so I already know how it ends. I'm going to prove that AC is congruent to BD. And then therefore I can say by the definition of congruency, they're equal to each other. Okay, so that's how it ends. We just got to get to this step right here. So what's your thoughts? What do you mean start with it?
You said that you can start with saying you're the same distance from the line.
Well, the thing that we got and that you're referring to is that we measure distances between any two things perpendicularly. That's kind of what you're referring to. We never proved that for parallel lines, the distance never changes. We just kind of threw that out there. We're going to prove it right now. But you're correct. We always measure distance perpendicularly. All right. What's our basic scheme of maneuver for showing two things are congruent? What's our basic thing that we've been doing? See if there's triangles there, right? Show that the two triangles are congruent, and then call out CP, So let's investigate that. So obviously, I would want to draw what first?
A line through the middle.
Okay, where do you want to go from?
C to B.
All right, let's go from C to B. All right, now I got my two triangles. We could say it would be pretty easy to prove that this is 90, right? Makes a line, the other side's 90. We could easily prove that because these are parallel, right? That if this is 90, right, interior angles are supplementary, right? Same side interior. We could prove that's 90. Okay, I got two right. That's horrible, but I got two right angles. Now what? Bailey, look at the triangles and tell me why I'm calling on you. Bailey, if you haven't picked it up by now, I call on you every time because I'm still getting you to try to remember one thing and one thing only, and that's that. The same thing 5 minutes ago. What do you see? Where do you see that? What is the name of it? Just look at the two endpoints. What's the name of it? Okay, is reflexive. So we could say that's congruent. All right, can I prove those two triangles are congruent now? Anybody?
Not yet.
We need one more. What do you got? So we got alternate interior angles. We got that one and that one. The two triangles congruent. So are they congruent? They are. And you're done. Okay? So that's a pretty easy one to do. Now, the book chooses to do it a different way. And I got to show you this way because it's a new technique. So our old technique was we make what?
Triangle.
We show the two triangles are congruent. We call CP. Perfectly done. And by the way, you just proved that one. And I didn't even have to guide you too much there. You kind of did that one all by yourself. What's this chapter shape? What's the whole chapter on? Quadrilaterals, and we've been looking at parallelograms. Hey, guess what I really have right here when you draw this shape? I got a parallelogram. So this is technique number 2. Technique number 1, and it's the most one used in the book, make two triangles, show the two triangles are congruent, CP. If, however, I can show it's a parallelogram, I can say those 4 things. Opposite sides are congruent, opposite angles are congruent, same side or adjacent angles are supplementary, and which one did I leave off? Oh, I thought there were 4 of them. What was the 4th one? Opposite sides are congruent. Opposite angles are congruent. I'm at a loss here. Can't think of the 4th one. Okay, so that's what we're going to do right here is we're going to show that this thing is a parallelogram. Now, by the way, we already proved this one using your method, and it worked fine. All right, I could say that this one and this one are 90, really easy to do, right? Same side interior lines are supplementary. So I can show that this one is 90, that one's not, they're all 90, right? So it's technically a rectangle, we just haven't talked about what a rectangle is yet. Well, I can say it's a parallelogram. You want to know why? Because I just showed that this was 90 and this was 90. So that means that this one plus this one, therefore they're supplementary. So that's the way we can show. Oh, by the way, the other thing we can show is that opposite angles are, therefore there's a third way, right? So opposite angles are congruent, right? Therefore it's a parallelogram, right? That's by the definition, or not by, if both pairs of opposite angles, that's whatever that theorem is. I've already forgotten the number, okay? If it's a parallelogram, then what can you tell me about opposite sides? They're congruent, therefore we're done, right? So this is option number 2 now, right? Option number 1 is always go with your friends, the triangles, right? Right, they're the easiest ones to mess around with. We got a lot of things. Option number 2 now is we got something else. If you can show that the shape is a parallelogram, you can say some things. Now, the issue with a parallelogram is you got to do a little bit of thinking ahead. Hey, if I prove that this is a parallelogram, would I be able to say that this side is congruent to that one? The answer is yes, because opposite sides are congruent. Okay? So a little bit of forward thought to it, but here's option number 2. We got 2 techniques now. Yeah, for the most part, we're always going to do triangles, but occasionally in the book, we might get a parallelogram, and it's just as easy. Okay? All right. So there's our first one. Write this down, please. This is 5-8. We finally actually proved. Remember, I just picked 2 points at random. I could have picked any 2 points along the line. I just proved that if 2 lines are parallel, then all the points, no matter which one you pick, is equidistant to the other line. You pick 2 points at random on 2 different parallel lines. I should say, if you pick 2 points at random on a line, and you measure from that point to the other line, you got to measure it perpendicularly, then the measurements of those 2 segments that you just created are equal. It says, then all the points on one line are equidistant to the other line. Just remember, distance is measured perpendicularly. Mike is already reading ahead to the last proof. He's ruining my story. He's saying, I don't need it proved to me. I'm just going to use the last theorem and do my homework. By the way, that's exactly.
The second you said that, I'm just like, I can skip all of it.
Well, if this was not a geometry class, the answer would be yes. But it's a geometry class. I got to actually prove. I got to prove it's true. I can't just say, trust me, it's true.
I just love.
Well, it is true, by the way.
You.
All right.
I don't care.
We good on 5-8? Occasionally, once or twice in our book, you will call this one out. Hey, you got 2 parallel lines. The 2 points are equidistant to the other parallel line. Okay. So these are 3 of them in a row. The last one is the one that we're going to use. But these are a bit challenging. This is actually useful. We just don't use it much in class. All right, so here's the setup, right? I got 3 parallel lines, right? And I draw 1 transversal. And on this transversal, we measure it. We find out that this distance, AB, is the same as BC. That's the setup. That's what we're given. We're trying to prove this, that if you draw any other transversal, it doesn't matter how you draw it. It doesn't matter how you draw it. That if this is congruent to this on any other transversal, that this piece will be congruent to that piece. And this piece will be congruent to that piece, which is by the way, this is how they actually make rulers, is they do this, because this allows you to make things that are equidistant at a specific distance. Okay? I should say it's one way you can make a ruler. All right, so let's see if we can prove this sucker. So we need to prove that this is congruent to this. And why are we doing this weird proof is because this is what's going to allow us to prove the very last one. All right, so let's see what we got here. This is the part where I would be scratching my head saying, I don't even know what to do. This is pretty slick what they do. Here's what they're going to do. You're allowed to draw auxiliary lines anywhere. So they make two special auxiliary lines. They're going to go from X to this line right here, but they're going to make it parallel to this line. So they're going to go from here to here, and they're going to make it parallel to here. They're making a parallelogram. They're going to go from Y down to here, and they're going to make it parallel to BC. They're going to make a parallelogram. See what they did? Right? Can you see the two parallelograms? One here, one there. Notice, what else do you make when you make this parallelogram? What do you get right here? You get two triangles. So here's the thought, and it's way above my pay grade. They're going to say, hey, I can make parallelograms, so I can say something about the parallelograms. Opposite sides are congruent, opposite angles congruent. And then they're going to make two triangles. In order to prove that XY is congruent to YZ, they're going to show that this triangle is congruent to this triangle. Pretty slick. But they do it because they see two parallelograms here. You made that side parallel to this side. Well, you were already given that the top was parallel to the bottom. So you got a parallelogram, both. Now, they're not the same size parallelograms, but you get two parallelograms. So the very next statement is that, hey, you just made parallelograms. Great. So what? Well, the so what is now I can say something about parallelograms to help me prove that these two triangles are congruent. Wes, what do you think is the obvious statement?
Vertical, we use the alternate two angles. 1 and Y is congruent to 1. 5, 6 is congruent to 5.
I could use that, right? I'm just thinking about this red dotted line and that red dotted line. What could you immediately say? If this is a parallelogram.
Oh, they're
what?
they're parallel.
And they're also congruent. So I could say as my next statement, this is pretty slick. I can say that this piece and this piece are congruent. Why? Because it's a parallelogram. There's one tick mark here, so I can put one tick mark here. But wait a minute. The same thing I could say about this parallelogram. That tick mark is 1, and therefore that, hey, I just showed that these two sides of those triangles are congruent. Why? Because they're part of a parallelogram. That's crazy slick. Now, what was the other thing you wanted to say?
I want to say that you can say 6 equals 5.
I can certainly say that 6 equals 5 because they are.
Alternate two angles.
No, they're not really alternate here. They're.
You do alternate two and then you do vertical. 6 is alternate two.
It's way easier than that. Why is 6 and 5 congruent? They're not part of the parallelogram. They're part of the triangle. I got 3 parallel lines.
Same side.
Cut by not same side interior. But what can you say about this angle and this angle? They're corresponding. Hey, there's lots of corresponding up there. 5 and 6 are corresponding. Turn your head to the left. What about 3 and 1? They're corresponding. What about 4 and 2? They're corresponding. Now, you wouldn't probably know that you need this, but we need that. So we're going to make that statement. Oh, by the way, we can easily say that this is congruent to this because one tick mark, right? So I'm going to say what Wes said, which is that long statement right there. He said that 5 is congruent to 6. He said that 3 is congruent to 1. 4 is congruent to 2. And I left off that 3 is congruent to 4. That's a long statement. Remember what our goal here was to show that this was congruent to this. This is the toughest proof probably done all year. That's a lot of stuff. Watch the slickness here. What's this say? But it says, wait a minute, 3 is congruent to 1, so what could I immediately say? I could say that 1 is congruent to 4, right? Substitution, right? But this says that 4 is congruent to 2, so I can immediately say, well, I'm going to substitute for the 3, the 1, and for the 4, the 2. See what I did? Just a double substitution. So I could say that 1 is congruent to 2. Why would I want to say that 1 is congruent to 2? Because my goal was to show that With what we're congruent?
AX and
The two triangles. So I need to say something about 1 and 2. So congruent, congruent. And oh, by the way, what's this say? So what do we got? What do we got? We got angle, angle, side, right? Angle, angle, that's a horrible arc, but you got it. Angle, angle, side. So we just proved these two triangles. All this is slick. That's slick. The two triangles congruent. We were originally trying to show that, I'll erase everything now, that this piece was congruent to this one, and then we got it by CP/CTC. Crazy good proof, right? Could you do that proof? I couldn't do that proof. I mean, I can do it if you say, draw this, but I wasn't coming up with that by myself. No way, Jose. All right. So once again, we just did a very challenging proof, right? We don't even know why we're doing it. Why we're doing it is because it's eventually going to lead us to our last proof, which we're going to use. Okay? So write this down, please. This is theorem 5.9. 5.9, write this one down. And it basically says this. If you have 3 or more parallel lines cut by this transversal right here, you see this? And if this is congruent to that, then any transversal that you draw, any other transversal, the pieces will be congruent. It doesn't matter how you draw this second one. You can draw it vertical if you want. Guess what you can immediately say? That's congruent to that. If you go from way over here to way over there, that's a pretty messy drawing, but this piece will be congruent to that piece. Okay? It's pretty slick. Like I said, they use this in art a lot. This is how you get your perspective right. Is they draw a couple parallel lines. They make sure that their parallel lines make congruent parts on the one transversal, and they can draw any other transversal, and you wind up with congruent parts. We'll use it, I think, twice this year. On the proof we're about to do, one more between this and the final one. Say again? Oh, sorry. Well, you know, the words are kind of getting in the way a lot of times. The picture is what you really want to understand. You have 3, it's 3 or more parallel lines, and if you cut it with one transversal and create congruent parts, then any other transversal you draw will be congruent. Now, it's not saying that this piece is congruent to this piece, not saying that at all. But it's saying that if you create a transversal with congruent parts, then any other transversal will also have congruent parts. If 3 parallel, it should say 3 or more. 3 or more parallel lines are cut off congruent segments. They cut off congruent segments on one transversal, and they cut off congruent segments on every other transversal. It only drew 2, but it could have drew 50 of them. 2 left, 2 more proofs left. And the last one is the one that we're going to use, that Mike already apparently did his homework on, because the theorem is pretty easy. The proof isn't easy, but the theorem's pretty easy. And if this was an algebra class, we'd be done by now, because it's an easy thing. But I got to prove it to you. That's what geometry is all about, proving things. We good? Dan, you got it written down? Excellent. All right. Kind of a so what, it's neat, but you know, it will be useful to help us prove our very last one. All right, so here we go. Here's the proof. Here's the picture. You ready? Ready for the picture? Okay. If I take a triangle and I find the midpoint of any one of the 3 sides, any one of the 3 sides. So I'll just pick this one, right? I find the midpoint. And then through this midpoint, I draw a line that is parallel to this one right here. Got it? I find the midpoint of one side, and I draw a line through it. I make it parallel to the bottom. So kind of like that. That's the setup. Okay. If this is a midpoint, what can you tell me about this piece and this piece? Okay, so that's the picture. Okay, got it? So here's the midpoint, M for midpoint. All right. So this is congruent to this, and this line is parallel to this line. Okay, that's the setup. What we're trying to prove is that if you draw through the midpoint of one side to the other side, that it must, if this line is parallel to the third side, it must go through the midpoint of the other side. Kind of weird, right? But it must go through the midpoint of the other side. That's what we're about to prove, by the way. So we got to prove that this is the midpoint of AC. How in the world will we ever do that? Well, first off, how do you show that N is the midpoint? What's a way to show that N is the midpoint? What's the definition of midpoint?
Middle of something.
So how do you show that N is the midpoint?
Oh, that the distance from A to N and C to N is the same.
Okay, so if I show that AN is congruent or equal to either one, congruent to this one, then you just show that N was the midpoint. You buy that? If I show that AN equals NC or congruent, either one, then you show that N is the midpoint, and that's what we're going to do. Okay, so that's our technique of what we're going to do. What we're going to use is the previous theorem. So what are we going to do? The previous theorem had how many parallel lines?
3,
So how many parallel lines do I have right now?
2.
I'm going to make a third one. I'm going to make it go through A, and it's parallel to this one and that one. See what I did? Ignore my horrible, it didn't go to the top, but I really wanted it to. I couldn't make it. Yeah? What does the last theorem say?
If they cut off the congruent segment,
Hey, I cut off congruent segments. Then
they cut off every transversal.
any other transversal, do we have another transversal to these three lines? Here's one.
Yeah.
Oh, AC is a transversal. So what's the then part? Then
And then they cut off congruent segment.
Then this one, because of our construction, it must cut off congruent parts. So what parts are congruent? Oh, and by the way, we're done. That's what we're trying to do, was show that that is congruent to that. Therefore, we can say that the two parts are equal. And we're done. That was crazy easy. Once again, this is a so what proof. You'll never use this except on the next proof. One time in the entire book. But we had to prove this in order to use it for the next proof, which we finally got into the one that we're going to use. Okay. Write this down. 510. A line that passes through the midpoint of one side of a triangle, and that's parallel to this side, say the third side, it must go through the midpoint of the second side. Is that what it says? A line that contains the midpoint of one side of a triangle and is parallel to another side, pass through the midpoint of the third side. All right, they said it better than I did. There's no other option. If you pass through the midpoint of one side of a triangle and you're parallel to another side, it's got to go through the midpoint of the third side. It's got to. Why? Because there's only one line that is parallel to another line that goes through a given point. Right? The only way you get something to not touch it is to make a curve. That curve right there, we wouldn't say it's parallel to this line, but it certainly doesn't intersect this line. But since we're dealing, at least in high school geometry, with non-curved lines or curves, we're only dealing with lines, and lines are straight, and we don't have another option. Good. I said this one is not very useful. It'll be very useful for the next proof, just not very useful for the rest of the book. But this is how we're going to get to the final one. So the first one we proved, well, it was just basically showing that parallel lines always remain the same distance apart. But the second one and this one, right, the second one we used got us to this one, and this one will get us to the last one. All right, here we go. Finally, last one. This is the most useful one. Here, we got formulas. Finally, Mike already did his homework because it's that simple, right? But I got to prove it to you. All right, so I'm going to try to prove that if you have a segment that looks exactly like the previous one, it goes to the middle of two sides of a triangle, that this segment right here is half as long as this one. This one caused me problems in high school. I would look at this picture and I would say to myself, just visually, I mean, look at it. Does this look like it's half of this? Do you guys see that? It turns out it is. And even if you measure it, it's kind of an optical illusion. Does this look like it's half of that?
No.
To me, it never looked that way. And then the teacher would make me take a ruler and we'll measure it. And it ends up being it is. I don't know why. It's got to be an optical illusion of some sort. Okay, we're going to prove that. All right. Well, that's where we're starting. And we got to get to that they're parallel and that this is half of the big one. Okay. Got no ideas.
Auxiliary line.
Auxiliary lines must be, right? Well, it would be pretty easy to prove that it's parallel, right? Because of the previous proof. How many lines would go through the middle that are parallel to this one? Like, here's your one line. I'm going to draw another line through a given point. That's actually two given points. That is parallel to this one. How many lines could go through these 2 points that would be parallel to this one? Just one. And so we're going to call out the previous proof and the fact that there's only one line that can ever go through one point. Here, I got two of them, by the way. That's parallel to a second one. So I can immediately say that half of the answer right here, I can say that this MN is parallel to BC. I mean, simply because, well, it's called the parallel postulate. Through any point or through any line in a point not on a line, there's only one line that's parallel to it, right? Well, I got 2 points, right? Even better. And then Theorem 510 said that the line that goes to the two middles, right? Or I said the line that goes to the two middles is parallel to that one. Okay. Okay, so that part's done. I just got to get this last part and I'm done. Oh, there's a lot of space here. It takes a little bit of time. All right, so you said let's create an auxiliary line. Let's do that. So let's make an auxiliary line, right? This is crazy cool. I'm going to find the middle of BC, right? I'm going to find the middle of BC, put a dot, and I'm going to draw a line from N to that point. See what I did? I'm going to call it L. This is from the book, so if it looks off, it's the book's fault, not my fault. All right. Yes? Now, why would I do that? Well, you'll see it helps to prove. Could you come up with that yourself? I don't know. You have to be pretty creative to come up with that sucker right there. All right, here comes the magic. What did I say L was? So therefore, what can I say about BL and LC? So I could say they are congruent, right? So cool. So I could say they're congruent. Yes? Take your head. Tilt it 90 degrees to the right. So I took my head and I tilt to the right. Where is this dot coming from? And where does it go to? So therefore, this must be parallel to that for the same reason as this was parallel to that, right? Because it goes to the midpoint of two of the sides. And we just said, the previous statement, that if you go to the midpoint of two sides, you're parallel to the third side, Theorem 510. Okay? So I can now say that NL is parallel to, suspiciously, I'm going to say not BA, I'm going to say BM. So suspiciously, I'm going to say, oh, you got it, Wes. I just made a parallelogram. Okay? What was I trying to prove? I already proved that it's parallel. What am I trying to prove? That this piece is half of the whole darn thing. We just made a parallelogram. Harris, you can do this. It's a parallelogram. Do you see the parallelogram? If this side is 3 tick marks, what does MN have? Y. Magic hand, go to parallelogram. If this is 3 tick marks, she said then MN must be 3 tick marks, and I asked her why. She's flipping back to parallelogram. It's one of, I believe it's literally the second statement. What? You're on this page, this is parallelogram, yes? What's the second statement you wrote about a parallelogram? First statement should say opposite sides are parallel. What's the second statement say? Read it. Yeah, no, it would be before that. All right, help us out. If this is 3, why is this one 3? Yeah, but why? You can say the theorem or you can just say the statement, either one. I never remember the number. What? Opposite sides of a parallel are congruent. So if this one is 3, then that one's got to be 3. Okay? So I could say immediately that MN, I chose BL, I could have chose LC. MN is congruent to BL. Okay? Well, how did I get all that stuff? Well, I created this magical auxiliary line. And it turned out that I made a parallelogram. And parallelograms, opposite sides are congruent. Okay? Turns out I don't need to mess with this triangle at all. Right? One of the first proofs we're ever doing that we don't have to make a triangle. Okay? All right. Can you figure out the next statement? Yeah. I'm trying to get to that right there. I would like to say this. We got everything, by the way, in the picture that we need to make that statement. Seth thinks he's got it. Anybody else? What do you got, Seth?
So you just need to prove that 1/2 BC is BL and LC. And then once you say that, you can say that MN is.
So what would you like me to write?
Okay, so BL equals 1/2 BC.
I could write that. I could write that BL is 1/2 of AC. What allows me to do that?
Definition of midpoint.
Definition of midpoint, definition of congruence, either one of those would work, right? We already said these are both 3 tick marks. So he's saying BL is equal to 1/2 of BC. That makes sense. Now what do you want me to do?
And then you say MN is equal to BL.
Oh yeah, I like that. I like that a lot.
You just said BL is equal to 1/2.
Agreed.
And then you've got your statement.
All right. I chose to do it differently, but the same number of steps, but it's the same logic of what he used, but yours will work as well too. Okay. I simply say that MN, 2 of these would equal, 2 of MNs would equal a BC. Now, his was the same logic. He just chose to write it as half instead of, he would still need 2 statements. I still need 2 statements as well too. But I could say 2 MNs equal 1 BC, right? Well, that's just the definition of congruence or the definition of equality, any of that stuff. And then what am I going to do to both sides? To make that look like that. Just say it. Just divide by 2, right? So division property, and that's the whole proof. But yours would work as well. It's the same logic.
Excuse me?
Yes, ma'am.
Can you send Micah to the office?
He's on his way.
Thank you.
Bring back
That's why
donuts.
you got your homework done so quick.
Okay. So
Have a good one.
we got to wrap this up, and we got to wrap this up so that we walk away with this with our ability to do homework. We did a lot of stuff today. There wasn't, except maybe the first one. These are all really challenging proofs. This is the only one you need to remember. You need to have all the other ones written down, but this is the one you need to remember. This is the one that homework is all about.
Yep.
So write this one down. It is the only useful one, not the most useful one. And it says this: if you have a triangle where you have a segment that goes to the midpoint of 2 sides, then that side, MN, is equal to half of that third side. You get another statement too, and we did prove it. We proved that MN was parallel to BC. So you get 2 things. You get MN is parallel to BC. Okay, that's kind of useful. But the really useful thing, Chris, make sure you're writing this down, is what you need for homework, is that part right there, the one that goes to the 2 midpoints, is equal to half of the other side that it's parallel to. Who likes fractions? Nobody. So it would be easier to write this as what? Instead of writing it with a fraction, you could write it. Okay, agree. I'm just going to say let's just multiply both sides by 2 and write that. So some people would rather write it like this: 2 MNs equal 1 BC. But if you want to write it, this is the book doesn't write it this way. I just don't ever like messing with fractions. So I'm going to say 2 of the small ones equals 1 of the big one.
Can we just get our Zelda? Do it. Come on. Oh.
All right. There's only about 3 people in the room that got that. So.
Yeah, I know. He's all the sign.
All right. Tonight for homework, guess what they're going to have you do? They're going to give you this shape, and they're going to give you some numbers. And then you're going to have to interpret those numbers. You're going to use this picture and either one of these formulas. So we better check and see what that looks like. Yes? All right. Does everyone have it copied down? Let's see what homework will look like. By the way, this is all we did today. A lot of stuff. All right. 511 is the only thing that we're going to use of all of this stuff. So this is what homework will look like. They will give you a picture. It will look messy. They will give you some distances. And you will have to answer some questions. So it says P, Q, and R are all midpoints of the triangle. Notice there's segments joining all of those midpoints. So this will require you to turn your head left, right, and look at it straight.
Would it have to be on top?
It doesn't have to be. Right? It says, what is the shape of DPQR? Well, how do you know that? Because what was the first statement you just wrote down in 511? The segment that goes to the midpoint is the first statement. The segment that goes through the midpoints of triangles is parallel to the third, 511. We're looking at 511. So this goes through the midpoint. Then what can you say about this and this? Technically, you're saying about this and this, but this is part of that. This must be parallel to that one. You can do the same trick for this one. If this is parallel to this, then you have opposite sides are parallel. It's parallelogram. What's the perimeter? Bailey, this one's you. You see the parallelogram. What's the perimeter of this parallelogram? Well, we got to figure out distances. So the first thing we got to do is we got to figure out the distance from, well, I don't know, what do we want? Top, bottom, left, or right? Pick one. Top? Well, how far is DP? How do you know it's 6? Because it's at the midpoint, P to the midpoint, it's half, right? So this is 6. Well, how far is RQ? Yeah. From the theorem, the last one you just wrote. Why is it 6? I would accept 2 answers here. Why is it 6? What's the last theorem you wrote down? What does it say? Is this joins the midpoint. So what's the relationship between this and this? You got to read what it says in 511. And the second part, you didn't copy on the second part, did you? First part said it's parallel to that side. The second part, there was a formula. And that formula is what we're using tonight on every single problem. Help her out. What's the relationship between RQ and DE? It's a half. Remember the first or second day of geometry, I said, hey, guess what the math is going to look like in geometry? 2 plus 2. We're doing 12 divided by 2. The math isn't, the numbers isn't that hard, right? So this is 6. What was the other reason I could say it's 6, by the way? Opposite sides are congruent, right? Try it again, Bailey. If this side is 8, how big is this? It's what? I can't hear what you're saying.
8.
If this is 8,
Oh, 4.
it's got to be 4. And if this side is 4, what's this side? 4. And then you can do the perimeter pretty easy. All right.
Addition.
That was a lot of work for one thing, and that's the only thing you need for homework, yes or no? Yeah. Okay.
Yeah.
All right, e-learners, if you have any questions, speak now or send me an email. Nothing? Okay, I will see you guys tomorrow.